have this beautiful picture of this sort of pattern here going. Let's take some guesses. What do you got? 85 256. All right. Anybody else have any other guesses? What fraction? 1/3. 1/3. Anybody else? Yeah. 34%. We're doing fractions. 5/14. She says 5/14. Anybody else? Guesses are free. Anybody else want to like tally on? You know? Yeah.
I got 341
Out of 1,024. 341 out of 1,024. Good. Anybody other guesses out there? 7 over 20? Any other guesses out there? Really? 1, 2, 3, 4, 5. 30 people got all the same 5 things? Okay. For guesses? That's great. 1/2. Anybody else? 1/4. Sweet. Let's get one more just to fill out my table here. I mean, I made the table. Why not? 100%. Well, I know. 1. All right, sure. Why not? 1. Yeah, that's got to be it, right? 1. I'm sure that's the right answer. All right. Well, great. We're going to come back to that. We'll talk about that later. Let's begin our study of geometric sequences here, okay? So let's talk about what geometric sequences are, all right? A geometric sequence is a sequence with a common ratio. So instead of arithmetic sequences, it was a sequence with a common difference. Here we have an arithmetic sequence, which is a sequence with a common ratio, okay? So a couple things though, the ratio between any two consecutive terms is constant. That's what that means by having a ratio, and it is not equal to 0. Because after all, if two things divided by each other equals 0, then the top one has to be 0, and then that's not very exciting. The ratio between two consecutive terms is a constant. And we're going to talk about some of them in just a second. So that's what a geometric sequence is. It's a sequence with a common ratio instead of a common difference. And the ratio between two consecutive terms is a constant, and it can't be 0. So those are the important things that we have to know ahead of time up about a geometric sequence. Okay. Just like arithmetic sequences, geometric sequences are also recursive. So that means they build off of each other. Just like the arithmetic sequences did. So there's a general form for an arithmetic sequence. So this would be your general form here. Important. The nth term, a sub n, is equal to the previous term, and we represent that by a sub n minus 1. That's the previous term, multiplied by our r, which is our common ratio. So the general form for finding a geometric sequence for the recursive formula is just the previous term multiplied by r. So that's pretty important to have. Okay, so there's the front knowledge that we need. Okay, here's an example, right? Let's talk about this sequence. Whoa, I don't know what happened there. 1, 3, 9, 27, 81, ... Okay, so the first term is 1, the second term is 3, the third term is 9, the fourth term is 27, and the fifth term is 81. Yes, perfect. Okay, why is this a geometric sequence? Yeah. He says it's all multiplied by the same number, right? So you go from there to there, you multiply by 3. To go from here to here, you multiply by 3. To go from here to here, you multiply by 3. And from there to there, you multiply by 3. Why is it not arithmetic? Why is this not an arithmetic sequence? Yes, Mr. Dorn.
They're being multiplied instead of adding.
Yeah, we're multiplying instead of adding, right? So what would the common ratio be for this particular sequence? What would the ratio be?
3 to 1.
Yeah, the common ratio would be 3. I see why I said 3 to 1, right? Pick any term you want. Let's like the fourth term, which would be 27. And let's divide it by the previous term, 9, which gives us a value of 3. And that has to work for any two consecutive terms, right? I picked these two consecutive terms. It should work all the way across the sequence. Okay, so there's our basic example of a geometric sequence. All right, I have these two examples here. What I'd like you to do is think about whether they are geometric or arithmetic or neither, and then write out the first 3 terms and find the ratio or the difference. The ratio if it's geometric, the difference if it's arithmetic. I'll give you about 3 minutes to do with that negative thing. Okay. Okay, reminder. If you have 3 to the negative 1, it's equal to 1 over 3 to the positive 1, which is a third. If you have 3 to the negative 2, it's equal to 1 over positive 3 to the 2, which is a ninth. How does that play a role into what we're doing here? There's a negative exponent right there. So let's write this out. A sub 1, A sub 2, and A sub 3. What is the first term in black? 1/2. Yes, we take 2 to the negative 1 is 1 over 2 to the positive 1. Alex, what's the second term? 1/4, correct. Third term, Emma? 1/8, correct. Okay, guys, geometric or arithmetic now? It's geometric. Very good. So we say geometric. And what is the common ratio? The ratio is 1/2. Very, very good. Okay, let's do part B quickly here. What is the first term, Connor?
4.
The first term, he says 4. Do we agree? Second term? 16. Third term, everybody? 64. Okay, geometric or arithmetic? Geometric. Very good. And what's the ratio? 4. Nice job. Okay, everyone on board now? All right, sweet. Okay, we'll do one more box and then we'll take a break. Okay, just like before for arithmetic sequences, where you can like skip up to anywhere you want in the sequence, you can do the same thing for geometric sequences. So I call it the fast forward formula for geometric sequences, and you use it to find the nth term of a geometric sequence. So you got to memorize it. It's pretty easy. Here it is right here. A sub n is equal to the first term, which we call a sub 1, multiplied by, it looks like a comma, a sub 1, multiplied by your ratio to the n minus 1. That's it. That's not too bad, right? That's not too bad. You can memorize your phone number. You can memorize that. I don't know what my phone number is. Yeah, exactly. I knew where that was going real fast. I don't know. If you know your name, you can know that. All right. If you don't know your name, then you shouldn't be in this class. All right. What's my name? Okay, here we go. Let's just finish up with an example here. I'd like you to find the 9th term of this sequence, okay? And I'd like you to keep your answer in fraction form, okay? Here's the sequence I'm going to give you. 2, 2/3, 2/9, dot, dot, dot. Okay, so the first term, a sub 1, is 2. The second term, a sub 2, is 2/3. The third term, a sub 3, is 2/9. I would like you to tell me what is the 9th term without doing the American brute force way. Let's do the slick way. Like the French or something, I don't know. Are they slick? What's a slick country? Russia? You think Russia's pretty slick? Okay, let's be like the Russians. And do it the slick way. Okay, Mr. Quinn, can you please explain to us how you got 2 over 6,561, please?
I plugged in the numbers to the formula, so I put a to the 9.
A sub 9 is equal to, yeah?
2 times 1/3
1/3,
raised to the power of 9 minus 1,
which is 8. There you go. So find the ratio, which is a third, raise it to the power of 8, and then multiply it by 2. That is 2 times 1 over 6,561. Therefore, the 9th term must be 2 divided by 6,561. And it's easy as pie. You guys ready to do it? Okay. 6th box. we're going to add the first n terms of a geometric sequence. So we're talking about a finite amount, which means that the sequence ends somewhere. It terminates somewhere. All right? There is a way to do that. We're going to add the first n terms for a geometric sequence. And it goes like this. The sum of the first n terms of a finite geometric sequence is just the first term multiplied by 1 minus the ratio to the n divided by 1 minus the ratio. Now, the n, the exponent, is only on the r. It's not on the entire thing. It's only on the r. So it's 1 minus r to the n divided by 1 minus r. Very, very important. You got to memorize that. But you're going to do so much work with it that you're going to have it memorized in no time. 1 minus r to the n over 1 minus r. All right, let's use that here. In example 7, we're going to add the first 10 terms of a geometric sequence. And that sequence is this. 1 plus 3 plus 9 plus 27 plus dot 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 all the way up to a sub 10. Notice we don't even need to know what the 10th term is. Isn't that crazy? What are we trying to figure out here?
Yeah.
We're trying to add this sequence up. How much does this equal when we add this all together? So 1 plus 3 plus 9 plus 27 all the way up to the 10 terms of this thing, right? Now we could just go 1 plus 3 is 4, plus 9 is 13, plus 27 is... right? We could do that, but I could easily change that 10 to 100 or 1,000, and then we sure wouldn't want to be here all day. Unless you got time at lunch, we could be here and just do it one at a time. That's fine, but none of us want to do that. So here's what we're going to do. We're going to take the sum of the first 10 terms is equal to the first term, which is just 1, multiplied by 1 minus the ratio. Now, what is the common ratio here, everybody? 3. Very good. We're going to raise that to the 10th power and then divide that by 1 minus 3 because the ratio is 3. Notice we don't even need to know what the 10th term is. Okay, so we need calculators for this. Someone tell me, what is 3 to the 10th? So this is 1 minus 59,049 divided by, well, 1 minus 3, I can do that one. That's negative 2, isn't it? So that is, well, 1 minus minus that is negative 59,048 divided by negative 2. So notice we have a negative divided by a negative. The negatives cancel out to give us obviously a positive term since these numbers keep getting bigger. So how much does that equal all the way to the 10 terms? 29,524. Now that's way faster than sitting here, you know, and adding up one term at a time. But we could have done it. Absolutely. We could do it. We could do it all the way to 1,000 if we wanted to, right? Take a whole weekend. That'd be no fun though. All right. So we have a way to add up geometric sequences for the first n term. Let's say let me give you this. We're going to take you to what am I writing down here? What does that mean? What does that mean? So add stuff up, right? K is going to be 0 all the way to infinity of 1/2 raised to the k. Okay, so here we go. This is where we can actually talk about some fun things. What's the first term if I plug in a 0? 1. What's the second term? 1/2. What's the third term? 1/4. What's the fourth term? 1. Isn't it 1/8? Okay. And then plus keep going and go all the way. In fact, never stop adding. What does that equal? Okay, this is such an interesting time of our lives here. How many agree that it's bigger than 1? Well, that's true because it's at least 1. How many agree that it's at least 1.5? Right? Because there's 1.5. So it's at least bigger than 1.5. So if I add 1.5 and then 1/4, that's $1.75. So it's at least 1.75. Will this ever be 5? Will it ever be 3? Will it ever be 2? But how could it add up to something when we never stop adding something to it? Okay, we are adding a smaller amount, right? We're adding a very, very, very tiny amount every single time, right? Well, it turns out, so between 1 and 2, that's a good guess, right? But how many numbers are between 1 and 2? There's an infinite amount of numbers between a bounded region. How weird is that? This is where math starts to like get interesting, right? And it's not so boring anymore. Oh, Keith, I don't think so. Okay, because we're going to come back to it in a second. Okay, well, it turns out when you are adding a certain type of a ratio, and that ratio is between 0 and 1, or the absolute value is less than 1, sorry, I said it wrong. It turns out that you can add, it turns into a series. No longer called a sequence, it's called a series. So the sum of an infinite series, so here's what you have to know. If your ratio, the absolute value of your ratio is less than 1, then the sum of the infinite series is equal to a sub 1 over 1 minus r. So this is really important. This is the sum of an infinite series. Now a series is what you deal with when you add to infinity, no longer finite anymore. Okay, it's 1, and that's the first term over 1 minus the ratio. So let's go back and check to see if we can actually answer the question to this, okay? All right, what is the common ratio of this geometric series here? What is it? It's 1/2, right? So to add this up, so the sum of this geometric series is going to be the first term, which is 1, divided by 1 minus the ratio, which is 1/2, which is 1 over 1/2, which is 2. Whoa, exactly 2. So all this stuff sums up to 2. Crazy, huh? Well, what's really going on is the idea of a limit. And what we would really say is the limit as k approaches infinity is equal to 2. But that's for calculus class, and this is advanced algebra 2 trig. So for us, when we add all that stuff up, we can point to a value and say a value of. I'm at the beginning of the class. All right. Interesting. Now, there's 2 ways to look at this, right? Chris, you and Chris, right? There's 2 ways to look at this, okay? The first way is the finite way. No, you don't. Just follow. Just watch. And then the second way is the infinite way. Okay? So, how many of you at the beginning of class assumed that there were only 5 green boxes? Yeah. Here's number 1, here's number 2, here's number 3, here's number 4, and then there's number 5. There's 5 green boxes, right? Okay, so if you were to write this out as a sequence, because it's a finite way, the first green box represents how much of the total color. So that would be 1/4. And then you'd add to that, what about the second box? How much does that represent? 1/8? What is it? Okay, how do we get 16 from that? It's a fourth of a fourth. Good. What's the next term? What's this one represent? 1/64th, right? No. Isn't it 1/32nd? Oh, yeah. Oh, yeah. Well, the next one. Whew. 256. And then, well, this one. 1/1024. And then we're going to add those all up, right? So if you add all those up, who's done it already? What'd you guys get? Well, shoot. We don't have to, right? Can't we use this formula right here? Because that's the sum of a geometric sequence. 4. Okay, so we just did a bunch of math, and we came up with 341 over 1024 for the finite way. If we go back up to our guesses here. All right. Was that Caitlin? Yeah, Caitlin. Nice job, K, for you. How did you get that?